So we've already matched consumables to the application, and in those discussions, we briefly discussed extraction lenses. Here we're going to talk more about the flexibility the different lenses provide, along with additional parameters to get the most out of your mass spec. Agilent has 4 sources. The stainless steel source in the top left has existed the longest. In the top center is the inert source, which has a similar geometry to our stainless steel source, but is made of an inert metal. Next, on the top right is the extractor source. This is also called the inert plus, and that has an ability to use an E-tune to pull more ions out of the source into the quad. And finally, on the bottom is the high efficiency source, or the HES. We won't be discussing the HES source today, but that source is specialized for very low concentration detection. So how do you tell what source you have, especially since 3 of them have very similar front views and general geometry? So on the heater block of all sources, there are letters and temperature facing the MSD window, and this is shown best on the stainless steel source in the top left. The top line tells you if it's a stainless steel source, so it's SSI, inert source, inert's written out, or extractor, written as XTR, on the heater block. The second line tells you what type of ionization, whether it's electron ionization, EI, or chemical ionization, CI. And finally, the number on the bottom tells you the temperature limit of the source. So in this case, it's 350. So when in doubt about what source you have, take a look at the front of the heater block. Why did I say extraction lens and draw-out plate when talking about matching consumables for environmental analyses? Well, depending on the type of source you have, you may need a different part. For stainless steel and inert sources, a draw-out plate is utilized just after the source chamber. For the extractor or inert plus source, an extraction lens was designed in this place, which can have voltage applied to it, and this draws more ions out of the source and can lead to an increase in response with the use of E-tune. There are inert draw-out plates and extraction lenses in all 3 potential diameters, 3, 6, and 9 millimeters. Each lens or draw-out plate does better for specific analyses, as we briefly discussed before for semi-volatiles and pHs. Semi-volatiles and pHs and some other analyses, like using hydrogen carrier gas, do best with a 9 millimeter lens, while pesticides in food and your instrument checkout will work best with a 3 millimeter lens or draw-out plate. There are draw-out plates for stainless steel sources and inert sources. It's very important to keep these separated, and the inert draw-out plates are indicated with a small dimple in each lens, as shown in the 6 millimeter and 9 millimeter lens. So if you have both stainless steel and inert sources in your lab, it's important to keep the different style of parts separate. The inert parts should not be mixed with stainless steel parts, because that could cause different results in your chromatograms than expected. Moving further into the mass spectrometer details, we're going to talk about matching scan speed and gain factor to your analysis, and how we can use gain factor in diagnosing some potential mass spec problems. A question that can come up often is, what scan speed should I use for my analysis? And that answer depends on what your application requires: peak identification or quantification. First, knowing the chromatographic peak widths is important for setting your mass spec method parameters. Generally, the GC-MS chromatographic peaks range from 0.04 minutes or 2 seconds to 6 seconds wide. A test injection will give you a rough estimate of your peak widths. Note that a narrow column diameter or hydrogen carrier gas will result in a sharper and more narrow peak width. Identification requires fewer points across the peak, generally about 5 to 10 points, like the peak on the right side of the figure, while quantification requires more points, generally 10 to 20 points. So let's look at an example. On the left, we showed data points per peak, and on the right is the signal-to-noise ratio. These two characteristics of your analysis are interrelated to each other through scan speed. So we are showing results as a function of decreasing scan speed from top to bottom, which means that the quad takes longer to cycle through the entire scan range before starting the next cycle. This decreasing of the scan speed from n equals 0 to n equals 4 leads to a decreasing number of data points per peak from 48 data points when you have an n equals 0, in this case, to 3 data points when you have an n equals 4. On the other side of the coin, if we look to the right, decreasing scan speed leads to increasing signal-to-noise ratio because you're not sampling as often, so your signal-to-noise ratio gets better, which is great, right? Well, not necessarily. If you're trying to accurately identify or quantify a compound, you'll need more than just 3 data points. As usual, there are a good set of results to trade off between your signal-to-noise ratio and the number of data points for both identification and quantification. And for this analysis, the best scan speeds are around n equals 1 with a scan cycle time of 4.4 hertz, and that gives you about 20 data points and a signal-to-noise ratio of 2500, or n equals 2, which is about 2.3 hertz scan cycle time, and that's 12 data points with a signal-to-noise ratio of 4000. So a good place to start for most analyses is n equals 1 or n equals 2. So let's switch over to gain factor. Most of us probably use a gain factor of 1, but is that really the best gain factor for your analysis? So here's an example to help us determine our ideal gain factor. The ideal range for the most intense peak in an extracted ion chromatogram is 3 to 6 million counts. In this example, our gain factor is a little bit too high. So you can use the calculations shown on the right to determine a good gain factor. Input the current peak height in counts, so that's about 7.8 million counts, divided by the current gain factor of 1. And we set that equal to our target peak counts of about 3 million over our new gain factor. Rearrange it, and we get the new gain factor of 0.4. So let's try the gain factor of 0.4, and our peaks are in the ideal range, and right in the middle pretty much. So in this case, we had to drop the gain factor, but in other cases, you may actually need to raise the gain factor, especially for a tandem quad mass spec system, as those tend to run at gain factors of 5 to 10. But everybody's analysis is a little different. So talking a little bit more about gain and gain factor, instead of using very large gain values, Agilent converts those very big numbers into smaller numbers that are easier to visualize, hence the gain factor that you set up in your mass spec method. However, there's another gain factor used in the auto-tune of a mass spectrometer system. It's not the gain factor you set for your acquisition method, but it's the amount required to reach 500,000 counts for the 69 mass to charge ratio of PFTBA when used in tuning. Now, we won't go into overall detail of this tune gain factor, but it can really help you understand what is happening with the source and electron multiplier. We can watch the electron multiplier volts to understand how the MSD is doing, but it's also smart to watch the tune gain factor that's at the bottom of the report, and both the EM volts and tune gain factor are magnified from the report so we can watch them. If both the gain factor and EMV are increasing, typically this means the source is getting dirty. And in this example, we see the numbers increase together as the MSD was used with dirty samples. Now, what happens when we clean the source to our EMV and tune gain factor? But first, when we're speaking of cleaning the source, what's the best way to do that? First, disassemble the source completely and separate the parts to be cleaned. The filaments, nuts, gold screws, ceramics, and polyimide, those brown parts, are not to be cleaned in this process. We will only be cleaning the metallic parts of the source, including the extraction lens or draw-out plate if you have a stainless steel or inert source, the repeller, ion focusing lens, entrance lens, and the source body. Use cotton swabs and a slurry of distilled or deionized water and alumina powder or another non-bleached gentle cleaner to clean these parts gently back to a shiny surface. You do not need to put a lot of force behind these cotton swabs. A gentle cleaning does well. And try to avoid scratching the lenses, especially the repeller. If the surfaces become too scratched after many cleanings, the parts will need to be replaced. After using the slurry and cotton swabs, rinse the parts with lots of water. You can start with tap water and then finish rinsing with deionized or distilled water. The goal of this step is to remove as much and hopefully all of that alumina grit, so you can never use too much water in this step. Next, on step 4, is sonicating the parts in either DI or distilled water. Make sure there is enough water to cover all of the parts. Not enough water doesn't make sense. You won't remove all of the alumina grit if there's any left. And you'll sonicate the beaker of parts for 5 minutes. Steps 5, 6, and 7 are a repeat of 4, where we are sonicating in methanol for step 5 for 5 minutes, then acetone for step 6. Both steps 5 and 6 are to remove polar compounds. And then finally, step 7 is sonication in hexane, for 5 minutes to remove any nonpolar compounds. Next, we'll remove the parts from the hexane beaker and place them on clean foil or lint-free cloth to allow the hexane to evaporate from our parts. And then finally, reassemble the source together. But first, did you check the filaments? It's always good practice to replace the filaments before they fail. An unraveling EI filament, since it's usually coiled, or completely unraveled EI filament, and also discoloration on the metal behind that filament indicate that the filament will fail soon. Also, filaments near the end of their life can cause diminished response or odd artifacts in your chromatogram, such as negative dips in the baseline. So it's best to try to replace them before they fail. And also remember to replace your filaments in pairs. It's better to replace a filament a little too early rather than having a complete failure in the middle of the sequence. So let's go back to that tune report. We cleaned our source, we put it back in, we let it pump down, and now we're coming back and retuning it. So as we look at this new tune, the EM volts have dropped back to about 1200, which is a good number, and the tune gain factor is back to normal range of about 0.2. A good or normal gain factor usually sits about 0.2 to 0.4 for a single quad mass spec system. So our system's all clean and we're ready to go. So let's look at another case with our tune report where the EM voltage is increasing, but the tune gain factor is staying steady at 0.24. This generally occurs over months and indicates that the electron multiplier is aging. The electron multiplier horn is located at the back of the MSD analyzer. You have to remove the analyzer door to access the EM horn. The EM horn and high energy dynode are sensitive to electricity, especially static electricity and dust, so be sure to wear the grounding strap and lint-free gloves to handle any of these parts. The EM horn does not need to be cleaned or replaced very frequently. The source should be cleaned and retuned before jumping to replacement of an EM horn. So at the end of this journey, the system has new consumables matched to your analysis, a clean source, good gas flow, fresh wash files, and fresh rough pump oil or tip seals, and the GCMS system is back up and ready to run at peak performance.